L2 cache. For this machine, the cores share an L3 cache, which is also called LLC, the last level cache, because it's the last level on the processor chip before you go out over the pins of the chip to external DRAM, typically memory. Each level of cache is bigger and slower than the previous level, also cheaper, which is why you you try to optimize for the bargain components. DRAM is a bargain component. So each level, so how does this work? Okay, so when the processing core tries to access a memory location, it first looks for a copy of the memory location's contents in L1, which is closest to the processor and fastest. And if the processing core doesn't find a copy in L1, it checks L2. And if it's not there, it looks in L3. And if it's still not there, it goes off the chip to look in DRAM. And once the correct data is found, the memory system moves the data and all the other bytes in the cache block back down through the hierarchy, back to the processor. Now, several processor chips can be put on the same memory network. Memory network is different from a normal internet Ethernet type network. It's way faster, and usually you don't publish the interface specs. So if a memory access misses an L3, it can also fetch from the L3 and other processors instead of going to DRAM, because DRAM is slow. So let's do a quick poll here. So the point of caching is to overcome the slow speed of DRAM. So how many floating point operations can be performed by a high level, by a modern high-end processor in the time it takes to fetch a cache block from DRAM? Okay, so, oh, it doesn't look like the...
Give me 1 second, Charles, you skipped a question. Hold up. One second. I also turned on recording.
Yep, okay. So how many 64-bit floating point operations can be executed? So take a wild guess here. Got 22 votes. How many people do we have on the call right now? Doesn't show me when I'm presenting here. Let's
56.
See, 56, yep.
Counting static.
Yep. There we go. Okay, well, it turns out the answer is, is a lot. Whoopsie, sorry. The answer is a lot. It's 20,000. Okay, so it's the actually largest number that's there. And so you can see why it's important to write code that uses cache well, because you got 20,000 missed floating point opportunities whenever you have a miss. So a huge amount of effort goes into trying to accelerate getting things out of DRAM, and that's why we have a whole caching system and such. You can see, what does DRAM stand for? Does anybody know what DRAM stands for? You can answer in Slack. several people answering. Dynamic RAM. Yeah, dynamic random access memory is right. Okay, dynamic random access memory. And it's an amazing technology. Okay. Now, when I was a junior in college, a gigabyte of memory cost about $2 billion. Billion dollars, if you've seen that movie. Okay. And as you can imagine, as a student, I couldn't afford that. But today, a gigabyte costs about $3. You know, in comparison, the cache that resides on the processor chip is much more expensive and can cost 10 to 100 times more per bit. So DRAM is a bargain component. You build systems around bargain components. And it's really benefited from miniaturization and Moore's law. But even though DRAM still has a couple of more generations left, the cost per bit, you can see, is starting to flatten. We're no longer on quite the steep curve we had been for many, many, many years. Now, it's helpful to have a general idea of the parameters of a cache hierarchy. So here are some numbers that I grabbed from an Intel high-end server, the Xeon Platinum 8280L. So as you know, the memory system doesn't manipulate individual words. It moves things around in cache blocks, which pretty much on all Intel machines is 64 bytes long. If the data is close to the processor, it's in L1 cache, it takes 4 or 5 processor cycles, or about 1.5 or 2 nanoseconds to fetch it. It takes about 3 times longer to fetch from L2. And going to L3 takes 4 or 5 times longer than that. And if you miss cache completely, another factor of 3 more to fetch from DRAM. Okay, I tried to find out, but I don't know how long this machine takes to fetch from a neighboring L3. So I only could figure out what happened when it was actually accessing the different levels. And indeed, you know, performance numbers for your favorite processor can sometimes be hard to come by because the vendors don't really want to share performance information. Now, in addition to the sizes and the latency, I listed the associativity for the various caches in the table. And that's something I want to spend a little bit of time talking about, associativity. So let's review what associativity is all about, and we'll start with full associativity. So suppose that we have a W-bit address space. So most contemporary machines have W equals 64. And in this toy example, I'm showing the virtual memory on the left and the cache on the right. And this toy cache has size M equals 32 bytes. And its line and block size is B, and that's 4. So the total number of blocks that fit in the cache is 32 over 4, which is 8. So you can see I've got 8 cache lines in this cache. So by the way, what's the difference between a cache line and a cache block on Slack? Does anybody know what the difference between a cache line and a cache block is? Nobody typing? Some people are typing. What's the difference between a cache line and a cache block? Or is there no difference?
Full disclosure, I use them interchangeably, so I'll be surprised
Yep.
to see what you think the answer is.
Many people do, yep. Okay, well, it looks like some people are typing, but I'm not getting anything. Okay, well, let me spill the beans then, because we got to move on. Okay, so a cache block is the data that's moved around together. Okay, it's the data, and a cache line is the physical hardware in the cache where a block is stored. Okay, so the cache block and the cache line have the same size. Okay, so the cache line is the hardware. So a cache has a certain number of lines, and then a cache block is what you store in the line. And so those are the same size. But people confuse line and block all the time. And like Jonathan, I certainly do. If you want to have a little fun during lecture and do something that's maybe a little distracting, but not too much, keep track of how many times during the lecture I switch up the terms and let me know at the end, okay? So, because I'm trying to use it right all the time. And there are, of course, some people who are very careful about this. Most people are not. So there are 6 blocks in our toy cache, and 2 cache lines are empty. The arrows show which memory locations are actually stored in the cache and to which cache line they're mapped. So full associativity means that a cache block can reside anywhere in the cache. If the processor tries to access a memory location, it needs to search every line in the cache to see whether the cache block is there. Okay, because it could be stored in any line. And the cache keeps a tag for each line that tells which cache block, if any, is stored in that line. Okay, so that's extra bits that are coded. I didn't show those as being stored, but yeah, they're stored. Okay, and so you can see that the tags in the cache match the cache block addresses in the virtual address space. So for example, the first thing in the cache has a tag, which is just the address. Okay, now actually, I lied. That's not quite accurate. I guess we must have an election coming up or something, and that's in the air. So, so really, the tag doesn't need to store the low order log B bits. Okay, and the reason is because we're only indexing the cache blocks, and all the cache blocks, you know, start on with 2 zeros at the end. So you don't really, in this case, or in general, log B zeros at the end. So you only need a tag that is W minus log B bits. And then the other log B bits are used to index the offset in the cache, but they don't have to be stored in the cache. Okay. The hardware typically speeds up the search for a tag using content addressable memory. Okay. That's a parallel circuit that allows all the comparisons between the tags and given byte address being searched for to occur simultaneously. So it does a big parallel search across, okay, the entire cache for whatever is the byte address that it's looking up, the address of a cache block. But content addressable lookup is slower than simple table indexing, which is what you do when you index an array. Okay, or, and we'll see in a moment, that's what a direct mapped cache does. Okay, so here's So because the memory is much larger than the cache, as the program runs and the cache blocks are brought into the cache eventually fills up. When it's full, something has to be evicted to make room for a new block. The replacement policy is what determines which other block is kicked out. And researchers have studied lots of different replacement policy. So you probably have heard of LRU. The LRU replacement policy evicts the block that was least recently used. So speculating that, well, if a block hasn't been used in a while, it probably won't be used soon in the future. As I mentioned, there are a lot of other replacement policies, okay? So that's a fully associative cache in a nutshell. So are there any questions? Okay, let's see. So each row of the cache in this image stores 5 addresses worth of data. Yeah, in this case, we're saying it stores 4 bytes because the block size is 4. Usually, you know, in most like Intel processors, the cache line is 64 bytes. And so it can store 8 doubles, for example, okay, or 16 you know, floats or whatever, 32-bit data. Okay. So that's fully associative cache. So its main disadvantage is that it has to, you have to search, you know, throughout the whole cache in order to find something. And that makes it, that's a scalability issue. Okay, so at the other end of the spectrum from a fully associative cache is a direct map cache, which I'm illustrating here. So as before, we have M over B cache lines, each of B bytes, so a total of M bytes in the cache. And for this scheme, each cache block in the virtual memory always maps to the same specific location in the cache. Which I've shown here using 8 colors, each representing a different line in the cache. Now, I'm sorry not to have compensated for any of you who are colorblind, but I hope you'll still be able to follow. So feel free to ask questions if you have trouble. Basically, there's 8 colors there, even if some of them look the same, okay? Now, all of the same colored virtual memory blocks form what's called a set, okay? Since each block in the red set maps to only the red cache line in a direct map cache, and then also each block in the orange set maps only to the orange cache line, and so forth. You never have an orange block being mapped to a red cache line. Every memory location has a specific place in the cache. And that makes it easy to find whether a particular block is in the cache. The hardware needs to check only the one cache line where it possibly could be and check its tag. Okay. So much cheaper, more scalable hardware. Okay, now the indexing calculation for a direct map cache is faster and takes less hardware, okay, certainly than a content addressable lookup, which is what fully associative caches use. So for a direct map cache, the tag is shorter than for a fully associative cache. So it's actually W minus log M bits rather than W minus log B. Okay, the low order log B bits still form the offset, but now there are log of M over B, which is log of M minus log B sets. Okay. And so this scheme is good for spatial locality. across, I mean, the fact that you're keeping things on a cache line is good, but if the program accesses a small collection of adjacent cache blocks, such as the variables in a stack frame or the fields of a small struct, the hardware ends up mapping all the blocks to different cache lines because their addresses differ in the set field. Okay, so as you sort of march through memory linearly, you change the offset and then you go to the next set and then you change that and so forth, okay? But if the program accesses blocks that differ only in the high order bits, because all the blocks belong to the same set, and only one block from the same set can reside in the cache at the same time, okay, then you know, so then you end up maybe reusing the same cache lines, okay? But the hardware is simple and fast. So any questions about direct mapped caching and how it compares to fully associative caching? Any questions? Okay, hopefully this is mostly review, so good, okay. Now what most processors employ today is a compromise called a set associative cache. It's a compromise between direct mapped and fully associative. The scheme is less complicated than it looks at first, and the idea is to put multiple cache lines into the same set and then associate, so to speak, just over the sets. So if each set has k cache lines, we call it a k-way set associative cache. Okay, so the direct mapped and fully associative cache are kind of the limits. If you have a one-way set associative cache, that's a direct map cache. And if you have an M over B way set associative cache, that's a fully associative cache. So typical values for K are small powers of 2. Okay, but I don't know if you noticed, but the L3 cache on the Xeon Platinum 8280L is actually 11-way associative. So it's not actually just extracting bits. Okay, it's got to do div and mod modulo 11. Okay, and you might wonder how they actually do the fast indexing for an 11-way set associative cache, because that's dividing by 11 isn't something that is nearly as easy as dividing by a power of 2. Okay, and so that made me pretty curious too, and I discovered it's based on really darn clever work from the University of Texas at Austin, which is a top school for doctoral research if you're so inclined. So Tim, can you paste the citation into Slack? So I'm not going to assign this as reading, but if you're interested, it's a really great idea they have here for really cutting down on the hardware and making it fast for doing arbitrary modulus indexing. But in any case, we're going to continue with our power of 2 example. So like a direct map cache, the virtual memory byte address determines the set, and the cache block can reside in any of the K lines in the set. So here you see that you know, anything that's yellow could lie in either of the yellow cache lines. Okay, anything that's blue could land in either of the blue cache lines. Now, to find a block in the cache, if you're looking for a particular block, the hardware needs to check the K cache lines in the set, which is more than for direct mapping, but it's far less than full associativity, okay? So it has to only check K, and that's presumably a lot easier. So here's how the address bits break down, and you can actually look at this on your own. I'm not going to go through it in detail, but you should take a look at it. So any questions about set associative caching? I don't see anybody typing, so I guess I'll move on. Hopefully that's mostly review. Okay, it's going to get hard soon, okay? Now, when we attempt to access a cache block, if it's in the cache, we call it a cache hit. And if it's not in the cache, we call it a cache miss. Since cache hits are good, we don't worry about them too much. We don't look to see why we were successful. We just pat ourselves on the back and say, hey, we got a hit, that's great. But cache misses cost performance. So it's helpful to categorize the different reasons for a miss so that you can adopt, if you know the reason for the miss, you can figure out what's the best way of adapting to try to reduce the number of misses. So the most innocuous kind of cache miss is what's called a cold miss. Okay. Here we've never accessed the block before, so no wonder it's not in the cache. Not much we can do about that. Okay. If we got to access it, we got to access it the first time. The one thing that we could do about that maybe actually is prefetching. Okay, so there is stuff that even the hardware does about that, but in some sense the caching system doesn't do that. The processor logic and memory controller does that. Okay, the second type of miss is a capacity miss. And that occurs when the block isn't in the cache because it was evicted due to the cache being full. We ran out of space in the cache. Okay. Now, we're usually looking at set associative caches. And what it means in the context of a set associative cache is that even if you'd had a fully associative cache, there would have been a miss. Okay. And so typically you can try to access fewer things, or you can buy a bigger cache. Okay. But it wouldn't necessarily, you know, it's not because the K-way set associative cache that we were doing smaller associativity that was causing the problem, causing the miss. Okay, it's because there isn't enough room. Okay, in some sense, that's okay. Okay. The real devil for serial programs are conflict misses. Okay, these happen when there was ample capacity in the cache, but the block was kicked out because there were too many accesses to other blocks in the same set. And that's where modifying the layout of data in memory might help performance. Okay, where you try to make sure that things that are going to be accessed at the same time don't fall in the same set. And finally, in a multi-core system, there's another type of miss that we have called a sharing miss. Okay, we saw this last time. In the last lecture, Professor Reagan Kelly spoke about sharing misses. And this is where a block is not in one processor's cache because another processor needed exclusive access to it and came along and invalidated it. And there are two kinds of sharing misses. A true sharing miss happens when the two processing cores access the same data in the cache block. Okay, that generally shouldn't happen if your program is free of determinacy races, because that is a determinacy race. You got two things trying to operating in parallel, trying to access the same thing at the same time. but it still could happen under the covers by the runtime system. So the runtime system is doing concurrent stuff as well. And a false sharing miss occurs when the two processing cores are actually accessing different data on the cache block. False sharing, which we talked about last time, as I mentioned, is nasty because it's hard to detect. You can't readily see it in the source code. You're accessing this variable here, that variable there. Oh, they ended up on the same cache line, and the variables end up being accessed by different processing cores. But if you can diagnose false sharing, you can do things like padding and using other tricks to relocate the data onto separate cache blocks so that doesn't happen. So there are just a few tips of what you can do and why it's important to understand and taxonomize your type of miss. Okay. So I want to, for serial code, conflict misses, as I mentioned, are the real bugaboo. So let's take a look at some of the issues that can arise. Okay, and in particular, they often arise when you're caching submatrices of a matrix. Now we've written a bunch of code. Okay. So I have a question. How would the runtime system cause a true sharing miss without a determinacy race? Well, it turns out that the runtime system is full of determinacy races, but it insulates you from your code being non-deterministic. It encapsulates the determinacy race. So for example, whenever there's a steal, there has to be a race because you're trying to have, two processors that might each be trying to steal some work or whatever. And that's a determinacy race. It might not be, hopefully, a data race, okay, because you've got a lock to ensure atomicity, but it is a determinacy race, okay? And so that's why underneath the runtime system could have determinacy races, okay? But you wouldn't necessarily see that. Okay, back to submatrices. So here we have, so we've seen submatrices of a matrix. That's a very common paradigm, especially for scientific computing and numerical linear algebra. Here we have an underlying matrix of 1,024 columns by some number of rows. It doesn't really matter much how many rows there are, okay, of doubles. Okay, so 8 bytes. And somewhere inside is a 32 by 32 submatrix A. And the row width here of the underlying matrix is therefore 2 to the 10th, which is the 1024, times the size of a double, which is 2 to the 2 cubed, 8. So that's 2 to the 13th bytes. Okay. Now, let's assume that we have a pretty typical L1 cache, say, and the word width is 64 bits. The cache size is 32. Actually, this should be kibibytes. Okay. And the line and block size are 64 bytes. And we have, say, 4-way associativity. Those are pretty typical numbers for processors. Okay. Now, if you think about it, that means the submatrix A comfortably fits into the cache, okay, because it only has 32 by 32 elements times 8 bytes, and that, if you multiply it out, is just 8 kibibytes. And the cache holds 32 kibibytes. Okay. So kibibyte, by the way, I think you probably know is when it's 1024 rather than kilobytes is when it's decimal thousand. Okay. And once again, I often say kilobytes when I actually mean kibibytes. But anyway, I'm trying to repair my evil ways, to mend my evil ways. Okay. So if the program, let's say the program accesses this submatrix repeatedly, okay, then you'd expect that it would stay resident in the cache. There's plenty of room because the cache is 32 kibibytes and the submatrix is only 8 kibibytes. Plenty of room, okay? Now, if we map out for these particular numbers what the virtual memory byte address looks like, okay, it looks something like this, okay? There's 51 tag bits and 7 bits for the set and 6 bits for the offset. Okay, so that's what we get when we crank through the math with those parameters. Okay, now let's analyze this a little bit. And what I want to do is start by taking a look at a column of the submatrix A. Okay, so 32 doubles that are in a column. Okay, let's say, so what addresses does this column represent? So let's say the address of the first element in the column is X. Well, the address of the second element in the column is X plus the underlying row size, or X plus 2 to the 13th. Okay. And then for the next element, you add another 2 to the 13th. And then every element, you basically are adding 2 to the 13th all the way up through all 32 elements. Okay, that's where they each start in memory. Now, what's interesting about these elements? Can somebody talk on, answer on Slack? What's interesting about these elements? X plus 2 to the 13th, for whatever X might happen to be. X plus 2 times 2 to the 13th, and so forth. What's interesting about those? Yeah, yep. So they all have the same set. Yep, because the set size is a divisor of 2 to the 13th. So if you think about it, the low order 2 to the 13th bits, well, that's how many bits we have in the set and offset. So when I add 2 to the 13th, that's the lower bit of the tag. So I add 1 to the tag, and then I add another 1 to the tag and another 1 to the tag. I'm incrementing the tag as I go down the column. Okay. And so I end up using the same set. Now the set has 4-way associativity. That's generally good, but I've got 32 elements I'm trying to store there. Okay, and although I may have a lot of cache lines here, okay, I'm still only using 4 of them, okay, for that column. Okay, and so the conflict misses to access this would kill us if we kept accessing it, even though the cache is plenty big enough. And this situation is even worse if what the program is actually doing is repeatedly striding through a column, because all the column elements fall into the same associativity set. So It starts out at the top, and by the time it gets to the bottom of the column, the top is no longer in cache. And so if it keeps repeating going through a given column, as you might do in something like matrix multiplication, every access would cause a cache miss. I wouldn't get any hits. Okay, I wouldn't get any hits from striding through the matrix multiple times, through striding through the column multiple times. Okay, now there's some solutions to this. One solution is to copy A into a temporary 32 by 32 matrix and access the elements there. And that actually can be a very reasonable thing to do if you're doing it frequently enough. Now the column addresses will differ in the set bits rather than in the tag bits. Another solution is to pad the rows so that the column address likewise change in the set bits. Okay, it is exactly this type of anomaly that it motivated people to look at non-power of two associativity, because the access patterns that cause conflicts misses are less likely to occur, okay, if you have a non-power of two associativity. And you can check out the Texas paper if you're interested. It's not required, but feel free to take a look at that. So any questions? Any questions? I think this, non-power of two associativity is pretty cool. It's, the circuits they're building them in hardware, but they're kind of like bit hacks. It's very cool. It's very cool. They're like bit hacks, but, how do you compute it? So any questions? Okay. Okay. Now, a good strategy for designing a program that uses cache well is to not worry about conflict misses to begin with. Just first, analyze it and understand it. Make sure that it's a good algorithm for a fully associative cache. And then modify that algorithm, okay, to handle issues such as conflict misses if they're a problem. Okay. The ideal cache model provides a theoretical basis for that first step of designing it to use cache well, assuming you have a fully associative cache. Okay. Okay. So here's the ideal cache model. Okay. It has only one cache, not a multi-level cache. Although you can have a multi-level, ideal cache, just the basic model doesn't have multi-levels. There's only one cache level with M bytes and a cache line length of B bytes. Okay, it's fully associative, and its replacement strategy is the best you could hope for. Okay, it's optimal, omniscient. Okay, you can imagine that what happens is when a cache block must be evicted, the hardware consults an oracle to choose the best, absolute best cache block to kick out. Okay, and it knows everything and it can see into the future. It kicks out the one that's going to minimize the cache misses of the whole program. Okay. That turns out to be the cache line whose next access is furthest in the future. Okay, you can show that it's the furthest one that's in the future is the best one to kick out. Okay, we'll talk about the reasonableness of this assumption in a moment. Okay, but that's what it's doing, is it's giving you the best possible choice. Okay, now there are two performance measures that we'll care about, and one we have seen is called work. Okay, it's ordinary running time. Okay, or T1 if it's in parallel, but if you're just running serial code, which is what we're predominantly going to look at today, it's just T for the work. Okay, and the second is cache misses, which we generally will denote by Q, because I guess cache and Q start with the same sound, even if they don't start with the same letter. But C is like way overused. In fact, we're going to get into trouble with B because we're going to get into trouble with variables. You'll see. Okay. Now, the idea of a clairvoyant, omniscient replacement strategy sounds like major nonsense with no bearing on the real world. But it turns out it's not, okay? It's amazing, okay? So the LRU lemma, which was proved by Danny Slater and Bob Tarjan about 35 years ago, provides a theoretical justification. Bob Tarjan is a Turing Award winner, okay? And he won it for data structures. If you look at who has the best performing data structures theoretically, and he had to guess whose data structure it would be Tarjan. Or if he didn't invent the data structure, he was the first one to analyze it and get the best analysis. So here's what the LRU lemma says. Suppose that an algorithm run on a given input incurs Q cache misses on a computer with an ideal cache of size M. Okay, so we have a cache size of M, and we've got Q cache misses when you run the algorithm. And now let's run the same algorithm on the same input, but on a computer with a fully associative cache of size 2M, where the cache uses the LRU replacement policy. Then the algorithm with the LRU cache, the slightly larger LRU cache, incurs at most 2 Q cache misses. Okay, that's what it says. And this is, by the way, these are codes, they're looking at codes that aren't actually looking to see anything about the caching they're using. They're just straight ordinary codes that don't look and say, gee, I wonder whether I'm running on a cache or not. Let me time things and behave differently depending upon my timings. Okay, they're deterministic codes. Okay, so we have these factors of 2, the 2 for the cache size that has to be twice as big, and 2 for the number of cache misses. But for theoretical asymptotic analysis, they don't matter, right? They get swallowed up in the theta or the big O or whatever, okay? So when we're analyzing things in the ideal cache model, okay, we can, for lower bounds, usually we choose the LRU scheme replacement strategy for analysis. And for upper bounds, we choose the optimal strategy, okay? But you're free to choose whichever one you want, because the answers aren't going to differ by more than a constant factor. But the ideal cache model gives us a good strategy for performance engineering. First, what we do is we design a theoretically good algorithm in the ideal cache model, and then we engineer it for performance, taking into account the non-ideal aspects of the real world, such as that real caches are set associative and not fully associative. And we program around anomalies such as conflict misses. There's another detail that we won't talk much about, but which has been studied, is that in fact, loads and stores have different costs. And there's some tricks to get better performance by treating them differently. Also, whether you write on something or not is whether it's clean or dirty makes a difference. But we're not going to look at those details. They affect things by a constant factor. When you engineer them, you may need to worry about it. But for getting a sense of, well, let's just get things into the ballpark. Let's just see whether we fundamentally have a good algorithm or not. And then we can engineer the details. And when you're comparing two algorithms, it's nice to have a simple model to be able to compare them in. So here's a key lemma for understanding how to design cache-efficient algorithms and programs. Okay, it's called the segment caching lemma. So suppose that a program reads a bunch of contiguous memory locations, which we'll call segments. Okay, and let's say there are of them, and the ith segment consists of S sub I bytes. Okay, and let's call n the total number of bytes. And we'll assume that n is less than 1/3 m, the size of the cache. So we're not going to, it can be basically the size of the cache, but not quite. And what that means is that in principle, the number of bytes in all of the R segments fit into cache. Okay. And what this theorem says is that not only will they all fit into our ideal cache, which is fully associative, but also that if a program reads them all, okay, it incurs at most 3 n over b bytes. Now, before we prove this lemma, let me first comment that to read n different bytes, you've got to have at least n over b cache misses. Okay, if no data is initially in the cache. Okay, so to read n different bytes might take you more if they happen to be all on different cache lines, but the best you can do is squeeze them onto n over b into n over b cache blocks, I should say, not cache lines. Caught myself there. Okay. So the segment caching lemma says that you incur at most 3 times more than the minimum possible. Okay. Now for asymptotic analysis, okay, it says that if the average size of a segment is at least as long as a cache block, and they all comfortably would fit into the cache based on just comparing the sizes, you can treat them as if they were, as if they were all contiguous, and you get the best, they all fit, and you can access them the way you could if they were all just contiguous. Okay, that's kind of what it says. Okay, if you understand the statement of the lemma, which takes a little study. So a lot of this stuff, it's elementary in terms of the math. I mean, the math is just a little bit of algebra or whatever, but there's a lot of stuff floating around, M's and B's and N's and R's and S's and I's, right? That's a lot of things to keep in your head, okay? So it may take a little bit of study. Let's first figure how many misses occur when we access the ith segment, bringing into cache, presumably, if it isn't there already. So this, I have a little picture there in the lower left. So S sub I begins in one cache block and ends in another, spanning several cache blocks in between. And so how many cache blocks does Si reside on? So there are at most Si over B blocks in the middle, plus 1 block on each end. So accessing Si incurs at most Si over B plus 2 misses. So let's just add up the cache misses for all the segments. So the sum of the Si is just n. So we have n over B plus, we add up 2 from I equals 1 to R, that's just 2R. So we have n over b plus 2r. And now let's multiply the second term by b over b. Okay, so we end up with 2rb in the numerator and b in the denominator. And now observe that what is rb? By our assumption here, n over r is greater than or equal to b. So that means n is greater than or equal to RB, okay, or RB is less than or equal to n. So I can just replace that, and I get the second to last line here. So it's n over b plus 2 n over b. Oh my goodness, that's 3 n over b, okay, and that's what we wanted to show. Okay, so that's really helpful because it says, if you look at things that are segments and you're looking to see what adds up, check that the segments are the average length of the segments is larger than a cache block. Okay, and if they are, then you can treat them as if you did the obvious thing. Okay, so that's the end of the proof. So any questions about that? Any questions? Okay, let's move along. Not a lot of questions today. Okay, now much of the analysis of caching assumes that caches are tall, and this assumption comes in a bunch of places, including when you look at matrices, but also interestingly comes in sorting and so forth. Okay, so the tall cache assumption says that b squared is less than a constant times m, where the constant is less than 1. Okay, but what does that mean? What is a tall cache? Okay, well, the idea is that if you draw the cache as I've been doing, stacking the cache lines one on top of each other, where each byte is a unit square, then the height of the cache would exceed its width. Okay, that's because there's m over b cache lines, and that is therefore bigger than b, because m over b is the height and b is the width. And so another way of saying that is that b squared is less than m. And for the analysis, you may need to say that b squared is, for example, half of m or a third of m or whatever. It fits comfortably into the cache rather than tightly into the cache. And usually in analysis, you get to choose c, okay, yourself. Okay, so you just have to choose c, where c is some number that is sufficiently small. Okay, so that's the tall class of cache assumption, and in the practice, this is usually satisfied. So, for example, on the high-end machine we've looked at, the cache line length is b is 64 bytes, and the cache size m is 32 kibibytes. And so what that means is that b squared here is therefore 2 to the 6th times 2 to the 6th, which is 2 to the 12th. That's 4,096. Well, that's 1/8 the size of m. So that would satisfy it with constant 1/8 or slightly bigger than 1/8. Okay. Now, and then all the other caches, in the thing are way bigger, way taller. Okay, so this is a very common and easy assumption to have. Now, a notable exception is TLBs, which are a kind of cache, and they tend to be short. And it's one reason that TLBs are hard to deal with analytically, and they drive programmers, performance engineers, nuts. Okay, now why do we want tall caches? Okay, so submatrices, it turns out they're used in a bunch of different things, but submatrices provide one answer. So this picture is comparing an n by n submatrix of bytes, which I'm showing in blue, with an m over b by m over b short cache. Okay, so suppose the cache lines are in this case, way longer than n. Okay, so even though n squared might be smaller than m, considerably smaller, right? If you look at the area of the, what color is that? Chartreuse or something, compared to the blue, it should fit in there, but it doesn't, because each row of the submatrix shares its cache block with a bunch of data that we don't care about to work on the submatrix, but which goes along for the ride. So in contrast, if the cache is sufficiently tall, then if the submatrix has at most cm bytes, it fits into cache. Okay, so that's the nice property, that you can guarantee that it fits into cache if the cache is sufficiently tall, as long as as long as your number of bytes in the submatrix is small enough. Okay, this is the actual workhorse lemma that we tend to use when analyzing submatrices. And once we have it, we'll be able to analyze some algorithms. So assume that we have a tall ideal cache, and we have an n by n submatrix A that's read into it, where n satisfies this sandwich inequality here. Okay, n squared is at least cm, but it's smaller than 1/3 m. Okay, so the size of the matrix A is approximately the size of the cache, but not too big and not too small. Okay, the lemma says that A, and we get to pick C, by the way. The lemma says that A fits into the cache, and the number of cache misses is what you'd expect, about n squared over b. And as we know, it can take less than, it can't take less than n squared over b, okay, if none of it's already in cache, because that's what it takes if they were all optimally packed. And this lemma says it won't take much more, okay, at most a factor of 3 more. Okay. So as with all these proofs, they're straightforward, but sometimes a little hard to get your head around all of what's going on. And so to prove this, we're going to use the segment caching lemma. Well, actually, I'm going to let you study this proof on your own because I want to do algorithms. So you can look at this, and basically it's a simple application of the segment caching lemma. Just because it's simple doesn't mean it's not hard, okay, to get your head around what's going on. Okay, it's elementary. It's just there's a lot of variables. So there's a lot of stuff going on. And also, I ran into a variable conflict. I've got little n and big N. But anyway, you can take a look. Okay. Okay, let's analyze a fun algorithm. Who remembers matrix multiplication? Okay, what a rich and important problem. Okay, linear algebra. Wow. Yeah. Yes, your project 2 runtime is just a factor of 3 more than the cutoff, right? No, we care about those constants, but for asymptotic analysis, it makes sure we're not off by factors of n or something crazy, right? We want to make sure that we're in the ballpark, then we worry about those factors. And of course, that's a lot of what you do in performance engineering. Okay, here's the triply nested loop to multiply 2 matrices A and B, computing the product C. And it's actually computing C plus equals A times B. You know, it's updating it. And the body of the loop nest indexes the 2 dimensions by hand. So if you look at that last line of text, you know, I'm doing the actual row major indexing by hand because it's just a little bit easier to do rather than using C's 2-dimensional array syntax. Okay, and let me warn you, we're going to have a little bit of a conflict here because I've got B being the size of being the matrix, and also we have the script B being the cache line. But I think we can deal with that. Okay. So I hope you won't get confused, but I think it's probably good. Okay, so let's analyze the work. Yeah, let's analyze the work, duh, you know, n cubed, we know that. Okay, so the matrix is stored in row major order, and let's now analyze the cache misses, okay? And assume we have a tall cache. So how many cache misses do we incur? Well, it all depends upon how n compares to the cache parameters, okay? So we're going to look at 3 cases. In this case, n is greater than m over b, okay? So what does that mean? That means that n is at least the number of lines in the cache. That means a whole column won't fit in the cache at the same time because each element of the column resides on its own cache block, separate from the other elements of its column. Now, because the cache is fully associative, we're not really worried about conflict misses, even though we're looking at a column as we did when we studied submatrices before. That was a different problem. Okay, we're now looking at a fully associative cache. Okay, so for our analysis, we're going to focus on matrix B, since that's the one that will incur the bulk of the cache misses. And since we have an ideal cache, we can assume LRU or optimal replacement as we choose. And for this, I'm going to assume LRU. So let's look at how this algorithm strides through the matrices A and B, but we'll only count the cache misses for B. So initially, I is 0 and J is 0. Okay, that's the set the outer loop, and then we stride, through K. Okay, incrementing K, and that takes us with accesses along the first row of A, the 0th row of A, I should say, and the 0th column of B. Okay, 0 indexing here. Now, every access to B causes a cold cache miss for a total of n cache misses for B. Not a problem. We expect if it's cold, we're going to have to, bring it in. Okay. So now we increment I. Okay. And sorry, excuse me, we increment J. Okay. So we now have I equals 0, but J is now 1. And the inner loop scans across the 0th row of A again, but it goes through the first column of B. Okay. Using 0 indexing. So since the ideal cache uses LRU, even though the scan accesses the same cache blocks as it did before, none of the blocks are in cache. Okay, they got evicted as we were going down the column. Okay, and so again, there are a total of n cache misses, and we do it again and again and again. For every column, the scan causes n cache misses on B. So we have, for a given value of I, we have a total of n squared cache misses on B. Okay. And now we move on to the second row of A, and we incur another n squared cache misses for B. Okay. And so we have to do that n times, and so that's n times n squared is order n cubed, cache misses. Okay, so that's not very good because that's what the work was, and cache misses cost a lot more than the work. We're spending all our time dealing with cache, and you can convince yourself that misses on matrices A and C due to other bookkeeping doesn't increase this number asymptotically. Okay, so the cache doesn't really help at all. Okay, for this example, I might as well have thrown away the cache and just access memory directly. Now, a good exercise is to practice your understanding is to analyze the cache misses when you swap the J and K loops. Okay, so I'll invite you to do that on your own. It's a good study. Make sure that you understand what's going on here. Okay, case 2, the matrix still doesn't fit in cache because n squared is n squared is greater than m, but the number of columns of B is now at most the number of cache lines. Okay, so again, we're going to focus on matrix B and assume LRU replacement. So what happens? Well, we go through things the same way. But now I have fewer than n, I've hit fewer than m over B cache lines. And so the cache, being smart, is going to say, and so I haven't kicked out the first ones. And so, boom, hey, that's great. Okay, I get hits for the next one. Okay, so this time I get hits every time I go, but then for the next one I have misses, and then I'll have hits again, and then misses, and then hits again. Okay, but I only miss every B columns. Okay, so and then I do it again, and we get the same kind of thing. So we end up with n rows times order n squared over B misses per value for I, and that's n cubed over b. So we actually saved a factor of b in cache misses, and that could be pretty important because the matrix B is exploiting the spatial locality. Okay, when it accesses something else in the same cache line, that's a win. Okay. Okay, but we're not exploiting temporal locality. Okay, now here we're going to exploit temporal locality if the matrix is small enough. So once again, we look at LRU, and the analysis is easy. Okay, we go across, and by the time we get to the bottom, hey, I can access everything, and I don't have to worry about it. Okay. So they're n squared over b accesses. There are some boundary cases between the cases we considered, but it gets complicated. You don't get matching bounds, so we'll ignore them. Okay, so we save a factor of b. Okay, we can do a lot better with a strategy called tiling. Okay, here's tiling. Okay, that's 6 nested loops. So what's going on here? Okay. So the idea of tiling is to break the matrices into S by S submatrices called tiles that fit into the cache. So how many people use tiling strategy on project 1? So let's take a Slack poll to see how many people actually use tiling, because we were doing similar stuff when we were doing the bit matrix, right? But we'll go on while people vote, and then we'll take a look. So the outer nest of these loops performs matrix multiplications using the tiles as elements, and the inner nest performs matrix multiplication on individual tiles using the actual elements as nests, as actual elements as elements, okay? So you can see the outer nest uses indexes I1, J1, and K1, which move in increments of S. So those indexes always refer to the upper left-hand corner of a tile. And the outer nests walk through the tiles of A, B, C just as if it's doing ordinary matrix multiplication. But in this case, when it needs to multiply 2 elements, that is tiles, it uses the ordinary S by S algorithm on the tile elements, which are indexed by I, J, and K. Okay, so to analyze the work, okay, not too surprising, it performs each tile costs us S cubed, but they're n over S by n over S tiles, and to multiply them to cost us n over S cubed. And so when you multiply that through, okay, we get, when you multiply that through, we get n cubed. Okay, so the work is still fine. Okay, when we analyze cache misses, we actually get a dramatic improvement. Okay, so let's pick S to be good, and I'm going to pick it to be around so that tiles just fit into cache, that it's order the square root of M, and this is where we're going to use the submatrix caching lemma. Okay, that implies that I can bring in I can bring in a whole tile and only get S squared over B misses per tile, even though it's doing S cubed work. That's great. Okay, and so when you add it up and count up the cache misses, it ends up being n cubed over b m to the 1/2, to the square root of m. Okay, and so that's a big improvement. Okay, you save a factor of square root of m on the cache misses, and m can be pretty big. Okay, so dramatic reduction, okay, by tiling. Okay. It turns out this is optimal, as Hong and Kung showed in 1981. And I want you to remember this for a few minutes because we're going to get back to it. Okay. Now, the problem with the tiling algorithm is that we have what I sometimes call a voodoo parameter, because it takes magic to get these, to tune S, okay, to get it right. Okay, you got to tune it, and if you tune it wrong, or your code gets old and it gets moved to architecture with different things, S can be the wrong value, and it may be a bad value to use. So it makes the code very non-portable. Okay. And what if you have two levels of cache? Well, you may want to tile both levels. Okay. So you can tile using S by S tiles for the larger cache and using T by T tiles for the smaller cache. Okay. And that gives us 9 loops with 3 nests of 3 loops each. Okay. Wow. And now if I have, actually they have 3 levels cache. So I actually need 12 nested loops. Oh my God. And there are other things that can happen where the caches aren't the same. So this is incredibly fragile. In practice, people rarely tile more than one level. They find the worst bottleneck and they tile it to alleviate it and hope that that's going to be enough. Okay, let's look at a completely different approach for minimizing cache misses, okay, which is divide and conquer, okay? So we've seen this. This is where we're going to divide things into 8 submatrices and do an addition. Okay, I think you've seen this. And here's the code. Okay, so in the base case, of course, it's I have n equals 1, but of course you would coarsen that if you're engineering it. And now these 4 lines are computing the upper left corners of the submatrices, okay, for the various quadrants, okay? And I've color coded them so you can see where it is. And of course, we've analyzed the work for this and we get this recurrence and it's got theta n cubed. Okay, so let's analyze it to see how efficiently it uses the cache. Okay, so before I do the cache misses, let me analyze the work because I don't want to do it with the master theorem. I want to do it with a recursion tree because that's how we're going to have to do it because the master theorem won't apply to the recurrence we get for cache misses. So here's the recurrence. I dropped the theta because the constants don't make any difference, save some clutter. And we build the recursion tree by putting T of n, the total work at the root. And now each time we expand that, always maintaining the invariant that all the work is represented. Okay, so we just replaced it with the right-hand side where we expanded into 8 subproblems of size n over 2. And then we expand each of those. And then we expand each of those and we keep going down until n becomes 1, at which time we have theta 1 work. And now to analyze this, we can add across, well, first of all, we observe that we go down log base 2n levels because we're cutting down level by level. And I have about 5 minutes more, so I'm sorry to run over, but it's recorded if you have to go. So here's the analysis. So it's basically got log n layers. And that means the number of leaves, since we have a branching factor of 8 at each layer, it goes 8, 64, etc. And so 8 to the height is 8 to the log n. That's the same as n to the log 8. Well, that's n cubed. All our logs are base 2, of course, because we're computer scientists, not electrical engineers. Okay, then we add across the rows, okay, the work at every level, and we get this growth. And at the leaf, we add up, we've got n cubed leaves times theta 1 work, that's theta n cubed. And we observe this is geometric, so the total is a constant times the amount of work at the leaves, that's theta n cubed. Okay, and that's one way we can analyze the work of the divide and conquer algorithm, okay, besides using the master theorem. In fact, this method is how you prove the master theorem. Okay, same work as looping versions, of course. Yes, great. Okay, now let's take a look at cache misses. Now we get a recurrence that's similar here, okay? The recursive thing, the second line in the case here is Q of n is 8Q of n over 2 plus order 1. That's the same as we get before, but the base case is different. And the reason is because once we reach a value n, such that n squared comfortably fits in the cache, we only need n squared over b cache misses, because multiplying the matrices of that size, even though we're going down more levels, we're not accessing any other elements than what are in there, okay? And so, you know, we get the n squared over b here because that's the submatrix caching lemma again. So we have stuff that's going to fit if it's sufficiently small, okay? And then that's what it's going to be. So what we're going to do is solve this recurrence, but we can't go down to n equals 1. So the master theorem doesn't apply here. We're going to use the recursion tree. So here's the recurrence again. I've once again dropped the theta around the 1. Okay, and here's the recursion tree. We start out with q of n, and now we expand that, okay, to using the right-hand side of the recurrence, same as we did for work. Okay, and then with the second level, same as we did for work, same difference, and so forth, all the way down until we get to the leaf. Okay, and the leaves have order CMB cache misses. Now I could have dropped the theta notation, but I kept it in to show just an extra step. So when you go back and look at this, you can figure it out. This is because n squared is going to be about CM, okay? And so therefore, the base case, the first line in the recurrence, is really something at that point like theta of CM over B, okay? And now how many levels is that we're doing it? Okay, well, you know, when we hit a leaf at the recursion, n squared is approximately CM. So n is approximately the square root of CM, just as that first line in the recurrence shows. Okay, so that means that the tree stops at log base 2 of the square root of CM levels before the program does, okay? And so what that says is that instead of going a full log n, we stop log base 2 of the square root of CM, which is half the square root of log, half of log of CM, okay? So that's where you get the height, okay? And now we can add up the number of leaves. And if you do that, okay, you discover that there are n cubed over m to the 3/2 leaves. And here I've dropped the c. Okay, so that's a lot fewer leaves than we had for the work. And now we do the same thing, add across. Of course, it's growing geometrically. We multiply it through, and we get this n cubed over b m to the 1/2 when you multiply the size of the leaves times what's at every, you know, times the number of leaves. And this is geometric, which means this is the answer, n cubed over b to the m, b squared of m, okay? And now, hey, that's the same as what I asked you to remember, okay? The same misses as with tiling, okay? Very cool, okay? So what happened to the tuning parameter S? Okay, well, there is no tuning parameter here. The algorithm didn't need it. It's oblivious to the caching parameters, but it still uses the cache optimally, okay? And so an algorithm like this is called a cache oblivious algorithm. Okay, and they were invented in the late, about 20 years ago. And I'm proud that I am the L in FLPR. And they have the property that there are no voodoo tuning parameters. There's no explicit knowledge of caches, and you passively auto-tune. Okay, so you don't have to do anything. It just handles, just fits itself to the size of the cache. And moreover, it handles multiple levels automatically because it's always, as it's going down, as soon as it fits in that size of a cache, you're good. And it's also good for multi-tenancy, where other people may be using the cache you thought you had. Okay. So the best matrix multiplication, well, I explained it does binary splitting rather than divide into 4 and doing 8 multiplies. You can apply this to parallel, and I'm going to let you, this is the Silk code, I'm going to let you just read about this. It turns out that what this theorem really says is that you can bound the P processor total number of cache misses by the one processor number of cache misses. And as a consequence, we're not going to go through the proof here because we're almost done. It says that if you minimize the number of cache misses for the serial projection, you also minimize it in the parallel executions. So that's a good property. Okay, and that's it. So sorry to have run over. I did have a lot to cover today. And next time we're going to do actually some cache oblivious algorithms. This was maybe one of the hardest conceptual lectures that that we have. So so any questions? I'm happy to take them.